Welcome, everyone. A few of my colleagues actually thought that they read the title too quickly, and they thought that this was a talk about preventing overfitting with machine learning. So if any of you are here because that's what you think it's about, I want to assure you it'll be just as interesting, even though it's about overfishing.
We do address overfitting. Well, not in this talk,
yes.
But in the thing.
Yeah.
Anyway, hi, my name is David Kroodsma. I'm the Research Program Director at SkyTruth, which is a small nonprofit that does big data analytics and uses satellites to monitor environmental challenges. The main project I work on is Global Fishing Watch, which is the main thing we'll be talking about today. My background is in physics and Earth system science. And I am both fascinated by and deeply concerned by the human impact on the globe, and very excited about the role of data in better understanding and addressing those challenges.
And I'm Amy Unruh. I am in developer relations on the cloud platform at Google. And so how this came about is I originally proposed a Google Next talk that was essentially on the same topic in terms of the underlying infrastructure that Global Fishing Watch is using. And so then after I'd proposed that, I attended an internal talk where I learned about Global Fishing Watch, and I was extremely enthused. And so we joined forces, and so you're going to hear about a lot of really interesting tech solving real world problems.
And so the first thing we're going to talk today about is Global Fishing Watch, which is this project. And we should say right away that Global Fishing Watch is a partnership between SkyTruth, where I work, Oceana, a oceans conservation nonprofit, and Google, which is one reason that I'm working with Amy.
But the slides don't seem to be advancing properly, by the way.
We see it right here, though.
Yeah, we see it on our...
You can just turn the laptop around.
There we go. All right. So we're going to talk about how Global Fishing Watch uses Google Cloud Platform products. And in particular, for this talk, we're going to focus on Cloud Dataflow, TensorFlow, CloudML Engine. They also use BigQuery and GCS a lot. And we'll also talk about how we can take what Global Fishing Watch is using sort of as a basis for doing something new to generate close to real-time insights about the things that they're tracking.
Okay, so Global Fishing Watch. So who here has gone fishing? Okay, it's most of you. Who here has been on an industrial fishing boat at some point in their life? Where was it and what was it? Okay. So I probably won't be able to find that boat, but in most of us, when we think of fishing, think of this. And this is what I do as fishing, and this is what most people do. But most of the world's fish are actually caught by boats like this. This is a picture of China. Each of these boats is about 100 feet long, and the way that China manages its fishery in order to prevent overfishing is they have a 3-month moratorium at the end on fishing, at the end of which everyone's allowed to go out, and this is at the end of the moratorium when all the fishing vessels are about to go out to the ocean. And so it gives you a sense when you can see all the boats at once, just what is heading out for you if you're a fish. And this is really remarkable, but this is not to pick on China. This is happening all over the world. And it goes out into the ocean and extracts fish from this shared global resource, and it's kind of an ultimate tragedy of the commons. And the reason we care about this is because fishing is such a huge problem. So about 1 billion people in the world rely on fish as their primary source of protein, but the oceans are very overfished. 90% of apex species have disappeared in our lifetime, so that's big things like shark and tuna. About 85% of the world's fisheries are either overfished, at capacity, or recovering from having already been overfished. And perhaps the most important number here is this one in 5, which is the amount of fish which we call IUU, or illegal, unregulated, or undocumented. Essentially, it's fish where we don't know where it came from. And if you imagine you have a huge shared resource and you're not even able to measure where 20% of it comes from, that's one of the reasons you're going to have an overfishing problem. At the same time, this is a problem which really requires a global approach. 38% of fish is traded internationally. 55% comes from developing countries with an export value of $60 billion. So in summary, overfishing is a huge problem, desperately needs transparency, and requires a global approach to address, which is why we developed Global Fishing Watch. So, Global Fishing Watch takes data from transceivers on boats, which broadcast their locations, and these are big industrial boats, not the small ones, and maps out how they're moving, and then identifies where and when fishing is talking. If you go to globalfishingwatch.org, you can look at our map. It's almost near real time, so it shows fishing from 3 days ago to 5 years ago, and it looks like this. It animates and shows you where fishing is happening, and it's really, I love looking at this, because every time you look at it, I see something new. You can see patterns of fishing along the equator, where there's upwelling bringing nutrients. A lot of tuna fishing happens there. You can say fishing all along the continental shelves, because that's where a lot of nutrients are, a lot of fishing is. You can see political boundaries, where a lot of some type of fishing vessels aren't allowed to fish within certain country waters, so they fish right along the edge of it. And you can also see where people don't respect the boundaries of different countries. Like you can see Australia right there. You can see fishing happening right along the edge of it. You can see in Africa people ignoring some of those lines. So I'm going to now switch to our website so you can see what it actually... So you can click on individual vessels. So this is actually our live website, and you can watch them move. So here I clicked on this one, which is the Kaiyang 1. So each of these, and I should explain, each of these little yellow dots is where we think a fishing activity happened. And so if you hit play, you can now watch where this boat is moving. And this is a Malaysian boat, the Kaiyang 1. It's a long liner, which means it sets long lines of hooks, sometimes as long as 100 kilometers, and then retrieves them. And so here you can see it moving back and forth across the ocean. All the other dots are where there's other boats fishing here as well. You can see interesting patterns, such as here's an island in the southern Atlantic. You can see fishing happening right along the edge of where the continental shelf ends, and you can see that there's clearly some type of physical property of the ocean where upwelling happens right along the edge, and that's where fishermen are directing their boats. And so there's all types of interesting patterns we can use to gain insight into how to better manage our oceans. So that's the tool, that's the exciting thing we've built. And we're going to spend the rest of the time here talking about how we built it, and hopefully then empower you to be able to do some of the same types of machine learning techniques. So the core technology to this is called AIS, which stands for the Creatively Named Automatic Identification System, which is something that all large fishing vessels are required to carry. And it's a safety mechanism. The idea is you broadcast your location so that other boats nearby can see where you are. This is very important in some parts of the ocean. Here's a chart of boats in the English Channel, and all of these boats want to make sure they see where the other ones are so they don't collide with them. If you're in a boat with an AIS device, it looks like this, and you can see, you can see where all the other boats are nearby you. It tells you the name of that boat, which direction it's headed, its speed, all types of useful information to help you not collide with it. These signals, though, they can be picked up by satellite and also by receivers along the land, terrestrial antennas. In the last few years, a few companies have launched satellites which collect this data, and we have finally been able to build a global database of AIS signals. And that is what we have been collecting at Global Fishing Watch and working with. Oops, that was back. The AIS message looks like this. It's an NMEA message is the type. There's a Googler who wrote a library that we use to parse it into a readable JSON file, and this is what it looks like. It has, information about the latitude, the longitude, the course, the speed, the heading, as well as some other information. And we get about 20 million of these data points a day. As you can see, like all other data graphs, it's going up because there's more now. We have about 500 million a month. In 2012, you're getting far fewer because fewer boats had this technology, and we had fewer satellites and fewer terrestrial antennas. So we're getting more and more data every month. Oh. And when you map out what all the boats in the world look like, it looks like this. There's somewhere between 300 and 400,000 vessels with AIS. This is all of them, not just fishing vessels. And about 80,000 of these are fishing vessels, and that's what we identify to determine fishing effort.
Okay, so this is a lot of data. When I started looking at it, I was startled to find that every day 15 gigs was getting dumped, of this data was getting dumped into Google Cloud storage. And so not only is a lot of data to kind of shuffle around, but if you're going to analyze it in any meaningful way, it requires a lot of compute power. And so Global Fishing Watch would kind of like to not have to worry about that, about shuffling large amounts of data around, about provisioning VMs when they need it. And so you can probably guess the punchline, Google Cloud Platform to the rescue. So what I'm going to talk about is the workflow that they're using and how they put together some cloud platform products to do what David described on that globalfishingwatch.org site. And I'm going to focus on, for this talk, on Dataflow and CloudML Engine, but they're also making a lot of use of other stuff, in particular BigQuery. And David's going to, and cloud storage. David's going to talk a little bit more about the BigQuery later. Okay, so this is kind of a typical workflow, and they actually have several of them that follow this pattern. So first of all, a lot of ship movement data, remember it's like about 15 gigs a day, is getting dumped into cloud storage. And then periodically, in batch mode, they're running Dataflow jobs to process this data, to transform it, to aggregate it. And the output of that Dataflow batch pipeline is features, using the term in the sense of input to a machine learning model. So they're outputting data that is cleansed and aggregated and transformed into something that they want to feed into a TensorFlow model. Okay, so then you can probably guess the next part of this workflow is TensorFlow and CloudML Engine. So they've got, the features are being generated, and then there are sort of three parts to what happens next. So the first part is generating the training data, of course, and as those of you who have done this kind of thing might know, that can definitely be non-trivial at times. David's going to talk a little more about that. And then they've built some very interesting convolutional neural nets to do classification. You'll hear a little bit more about those. So label the training data, train the model. So they're using CloudML Engine to do distributed training of the model, of the TensorFlow model. And then once the model is trained, they use it for inference. So to dive a little bit more into some of the pieces of this, so this is probably some of you who have been to talks that go into this in more detail, but for those of you who haven't, let me say a little bit first about Apache Beam and Cloud Dataflow. So Apache Beam is a unified model for building data processing pipelines that can handle both bounded and unbounded data, batch and stream processing. And Apache Beam is also a set of SDKs for building these pipelines. And one particularly salient point about the model for the purposes of this talk is the way that Beam does event time processing. So you can tell Beam, I want you to analyze this data with respect to the time it arrived at the pipeline, or you can tell it, I want to analyze this data with respect to when it was actually generated. And we need to do that latter thing for the Global Fishing Watch data. We want to say, do your analysis with respect to the time this was actually logged by the ship. So then Cloud Dataflow is a managed service for executing these beam pipelines. And one nice thing about it is that it supports auto-scaling, so it will provision workers up and down as it needs them while it's running a big job. Okay, so that was Dataflow, the middle green piece there. Let me talk a little bit about TensorFlow and CloudML Engine. So again, some of you have probably heard about TensorFlow in the past couple of days. This is an open source platform for doing numerical computations with data flow graphs. But in particular, it's particularly good for building and training deep neural net models. It has a distributed runtime. It supports auto differentiation. It was sort of built for deep learning. So CloudML Engine, which those of you who attended yesterday's keynote know has just gone to GA then, is a managed service for training, doing distributed training of your TensorFlow models with GPUs are now available, if you like, and then for serving the model once you've trained it. So we'll talk a little bit more about that later.
And I should note that we've been using these GPUs and see about a 10 times improvement in our model training and inference using the GPUs over the CPUs, which has been incredibly useful, especially right now. I'm actually having some back and forth with our machine learning engineer and doing lots of iterations on the model, and it's really helpful to have those fast processors.
Okay, so I just, that was a workflow that Global Fishing Watch is using, but actually it's much more general than that. And this is kind of a useful and common design pattern where you want to do, you've got a lot of data, you want to do a lot of pre-processing and feature generation, and then you want to train a model. And so if you do this all in the cloud, you don't have to worry about scaling up. You don't have to worry about shuffling very large amounts of data around. And that's kind of what this suggests. Do your pre-processing with Dataflow, send the result to CloudML to do distributed training of your TensorFlow model.
So I want to talk now about how we actually built the net and how we got the training data for it. So we have two main classification problems with Global Fishing Watch. One is vessel identity, so identifying what type of boat it is and what type of fishing it is doing. It matters a lot for conservation and for marine spatial planning, whether or not the boat is fishing with a trawling net, which drags along the bottom, or if it's fishing with these long lines of hooks. And they don't tell you what it is in the AIS message, so you have to look at how the boat moves to identify it. The second problem is identifying when they are actually fishing and when they're just transiting from one place to the next. So here you can see these are three of the major types of fishing boats. There's a trawler, longliner, and purse seiner. They move differently. There's some pictures of these large vessels. And your eye can see the difference, and so we can train a machine to see a difference as well. The hard part, in order to train this model, we had to get a few thousand examples of these boats. And we did that by matching the AIS data to official registries, which involved a lot of fuzzy logic and fuzzy matching. From that, we got a few thousand boats from which we were able to match identify a few hundred thousand boats. And I should add that we were also identifying non-fishing boats, because remember, all the boats with AIS, most of them are not fishing boats. So you have to be able to tell what's a tugboat, what's a long line fishing boat, what's a tanker. Second problem is identifying when the boat is fishing. And to do that, ideally, you would have some logbook from the captain that would tell you when and where they put their gear in the water. The problem is that, one, captains rarely want to give you that information. And two, when you get it, usually it's not exactly right. For instance, the latitude and longitude may be slightly off, or the timestamp may be in the wrong time zone. And so it's much easier and sometimes more reliable to just look at the tracks and hand label where you think they are fishing. And so this is what we did, and this was very, very tedious. I built a small JavaScript interface through PIPA, an open source platform for crowdsourcing, and then basically messaged everyone on Slack every day to tell them they had to do more tasks. And we made a little competition out of it. Don't let Christian crush us this week. And this went on for about 6 weeks every day until we had labeled a few 100,000 points. And this is one of the main things, about this machine learning techniques I've learned is that how, one of the major efforts is getting the training data and getting it in the right position before you can even do any of the fun model building. Our first algorithm on fishing was a simple logistic regression trained on the average speed, the average, the standard deviation of speed, and the standard deviation of course, and as well as those features squared across a few different time windows. The whole idea is, if a boat is moving slowly, wiggling, and changing direction, it's more likely fishing. And that model did relatively well in accuracy, overall accuracy, I think just under 0.8. But then we've decided we wanted to do both for the identifying specific vessels and for identifying this fishing effort, we wanted to build a neural network to do this because we thought it could do a little bit better. And the problem with using a neural network is just the sheer number of points. So you can think about it. Each, we want to look at the whole path of a boat, and so you take maybe 10,000 data points of where it's been, and for each of those data points, you have like 10 different features, such as the speed, such as the course, such as the distance from shore, the time of day, and you want to use all that information to tell whether or not what type of boat it is and whether it's fishing. So that's 10 features per point and 10,000 points. That's over 100,000 features. You can't easily run a fully connected neural network on that. So we built a convolutional neural net that does a convolution in time. And what that does is we have 9 of these convolutions, and that takes more than 100,000 features and brings it down to around 2,000 features. And then after that, we have 2 fully connected layers, and that brings us down to a little over a dozen different vessel classes. And then we have a similar architecture which figures out looks at each point and identifies whether or not we think it is fishing. This is the detailed architecture of the identification model. We're also identifying the length and the engine power and the weight of these boats. Obviously, I'm not going to go over this, but we're working on a scientific paper to write up these findings, and you will be able to read much more about that in the supplemental materials of that paper. So how does it work? It works pretty well. Here's a confusion matrix of how the classification does on our different classes. And so the top one, these are the different classes. The top one is cargo or tanker. A reefer is a type of cargo vessel for fishing. And so you can see it actually confuses it with something that you would expect it to, because they're very similar types of boats. But for fishing boats, which are all down on the bottom, it rarely confuses them with non-fishing boats. So we're pretty happy with this overall. And then the fishing, identifying fishing activity, it's a little bit better than the logistic model, and we're making some adjustments to make it even better than that. So it performs better than the logistic, which is good. And we can, for the first time, build maps like this, which is where we think trawlers are fishing in the world's oceans. And trawlers usually stay close to the coast because they drag their nets along the bottom ocean floor. So this is the map where we think all trawlers were fishing in 2016. This is longliners. They set drifting long lines out in the ocean, and so they cover all the oceans. And then purse seiners, which set these nets around schools of fish, often tuna, and you can see them fishing along the equator, as well as some of the, as well as off the coasts of some countries. Again, why does this matter? Why do we care about identifying where and when fishing happens? Well, here is, I shouldn't have showed that yet. Anyway, so this is a map of the Central Pacific in Global Fishing Watch. And I'm going to zoom into the country of Kiribati, halfway between, So the country of Kiribati has the world's largest marine UNESCO World Heritage Site. Can you see it on this map? It is right there. So even though it was a World Heritage, and this is from 2014, even though it was a World Heritage Site, fishing, industrial fishing was still allowed. So you see lots of these are yellow dots in it. However, on January 1st, 2015, the president of Kiribati decided to make fishing, industrial fishing illegal in this area, the Phoenix Islands Protected Area, or PIPA. And so all boats were going to have to clear out. And so the question was, could we use Global Fishing Watch to identify whether or not this new boundary was being obeyed? And I should emphasize, this is the size of California, that red box. Kiribati is one of the world's poorest countries. They have like one patrol boat for that entire thing. So imagine you have to patrol California with one boat. And so what we did is you kind of wait to see what happens. And now it's playing forward. This is a 2-month period time, and now we're into 2015, a little bit of 2014 still. And as we get into all of it in 2015, they clear out. And we know the boats didn't just turn off their AIS because we were able to track what happened to all those boats that left and saw that they actually went somewhere else and fished. And so it's really exciting that we're able to identify this park. Now, in a few months after it closed, a boat, the Marshall's 203, we saw fishing just right inside the line right there. And the Kiribati authorities were notified, and they went, and their one boat escorted that fishing vessel back to port. And they said, the captain, they went to the captain and said, you are fishing illegally. We want to fine you for doing this. And the captain said, you can't prove I was fishing. How do you know? I'll see you in court. And so they actually called up SkyTruth and Global Fishing Watch and said, hey, can you guys look at this boat, see how it was moving, tell us whether it's fishing or not. And we sent them basically something like this with an analysis on it, as well as the results of our fishing algorithm. They showed that to the captain of the boat, and he said, okay, I'll settle. And it resulted in a $2 million fine, which is about 1% of the country's GDP. And so it was, it was extremely, yes. So I also enjoy a lot of data science work on this. So once we have this big data set, there's a lot of, we want to be able to look in all different types of ways, but it's still several terabytes. And so we load it into BigQuery and then use various tools to query it in BigQuery to slice it in different ways. And this is an example. I do a lot of work like this. This is an IPython notebook I wrote to write a query to make this graphic, which it's not impressionist art. It's not, someone saw this and said, congratulations. But what this is the x-axis is the day of the year. The y-axis is degrees latitude. And so you can see when and where fishing is happening. You see we have a lot more fishing in the northern hemisphere. That's partially because of our data set. You can see people take the weekends off. That's what each of those stripes are. You can see that 3-month closure period I was telling you about in China. You see how that's right there. You can also see that China actually, people in China don't take the weekends off as much as in North America and Europe. And you can see other things. You can see that in Antarctica, there's very little fishing, and it happens only in the Antarctic summer. And what's exciting about this is every time I look at this data, I make a kind of a new discovery, something no one's ever seen before. And it's only possible because we have these big data tools like BigQuery that allow us to quickly slice this data in different ways. We also are starting to use Earth Engine, which is a Google platform that allows you to do calculations on very large rasters. And so we can actually make our data, turn it into a raster, and load it into Earth Engine, and then look at how it compares to various climatological or other types of global data sets. And this just shows where all the vessels from Spain fish. And actually, it's quite remarkable if you look at how much Spain is fishing all over the world's oceans. So,
Okay, so this is where I came into the story. So I wanted to see, this is obviously very, very cool stuff. So I wanted to see what would it take to basically build on top of this to see if we could generate close to real-time predictions of fishing activity as all this data gets dumped into cloud storage every day. So it turns out that the answer is yes. And it was pretty straightforward. I was able to do what I'm going to talk about in just a few weeks. And very little needed to be changed in terms of how I hooked into what they had already built. And so primary reason for that is very straightforward to take the Dataflow pipeline that we talked about earlier, that Global Fishing Watch has been running in batch, using to generate feature data, because Beam has this unified streaming batch model. It's very straightforward to turn this into a streaming pipeline. And so essentially all I had to do was to change the so-called sources and sinks, the inputs and outputs of the pipeline. So I did some work to stream data into the pipeline using PubSub, and then the PubSub, the pipeline was also modified to emit data to another PubSub topic. So streaming in, streaming out, but the logic of the pipeline could stay the same, and so that was really nice. It was really straightforward. And then I added a new pipeline that consumed that output stream and did some further derivations of using the derived features, and using CloudML engine and the trained TensorFlow model to make predictions about where fishing activity was happening. So this was the second of the two models that David was talking about, the model that predicts fishing activity. Okay, so what the second pipeline does is basically surface in near real time where are the fishing activity hotspots at a given time. So let me show you what kind of the result of that, and then I'll dig into the tech that made it work. Okay, so this is being displayed on Cardo, a cool site. This is data from real data from a couple of weeks ago, and when I hit play, what it's going to show is basically over the course of about 10 days, what fishing activity hotspots did we find? So the heat maps are just showing magnitude of fishing in the area. You know, might have been more than one boat, and over time you can see those shift around, and it's even a little more dramatic if I zoom out a bit here. Okay, so you can think of this as being, you know, in near real time as the data comes in, we're saying, all right, you know, there's fishing activity here, there's fishing activity here at a given point in time, and then we kind of have a sliding time window, and so that can help Global Fishing Watch give them indication if, you know, early indication if fishing is happening where it shouldn't, or, you know, if there's things they want to focus on in their larger batch analytics that doesn't look quite right in terms of where people should be fishing at a given time of year. Okay, so now let's look at what went into that under the hood. So here's the just kind of at a high level, the logic of the second pipeline that I built. So as input are these derived features from the first original Global Fishing Watch pipeline. And again, using features in the sense of input to their machine learning model. And David, remind me, what is MMSI?
Marine Mobile.
I can never remember that acronym.
Security number identifier.
Yes.
So it's Given out by the International Telecommunications Union to boats.
There you have it. There'll be a quiz. so each such identification, which corresponds to a ship, a stream of features is being generated for that ship. And so this new data flow pipeline first aggregates those for each ship into a sequence that's of sufficient length to send to the trained machine learning model. And it responds with indications suggested by the blue-colored cells here of where it thinks fishing activity is happening in that sequence. So we know the time where it thought fishing was happening. We know the location. So then, and we used the learned TensorFlow model and CloudML to do that. And so then, the next stage of this data flow pipeline groups this information by geographic region. So I'm using a representation called S2 geometry to group the detected predicted fishing activity into basically like 1 kilometer square areas. And so by doing that, we get an indication of like what's the magnitude. It might be more than one boat. What's the magnitude of fishing in a given area at a given point in time. And then, of course, we want to analyze this over time. And of course, the magnitude might change over time for a given square. Okay, so to do this, now let's start to look at the nuts and bolts a little bit. The first thing we did was compose the two data flow streaming pipelines, connecting them by pub/sub. So the first original feature extraction pipeline, and then this new pipeline to use CloudML engine to do prediction of fishing activity, and then to do basically location-based clustering. So this is a really useful pattern. You can kind of think of data flow pipelines as like, decomposable chunks of logic, kind of like modules, and actually almost kind of reminiscent in how you hook them together of Unix pipes as well. So you can compose them together. You just need to connect their inputs and outputs, essentially. And the data flow pipelines can have different owners. They can even be in different projects. They can be written in different languages, and that was actually the case here. The original pipeline was written in Scala, and the one I built was written in Java. And then the means of connection is pub/sub. So something to keep in mind then is that Apache Beam's unified model for doing both stream and batch processing lets you use these pipelines that you build in different contexts. Do you want to hook them together in stream mode? Do you want to use them in batch mode? You can use essentially the same pipeline for both. Okay, so another key thing that we leverage to do this is Apache Beam's windowing model. So if you think of you've got an unbounded, essentially infinite stream of data coming in, and say you want to and say it's colored tiles, kind of like what's suggested up top there, and say you want to group them by color. So you want to group all the green tiles together and count them. You want to group all the yellow tiles together and count them. You need to do that in the context of some defined window, or else it's ill-defined. It's an ill-defined problem. So Apache Beam has really sophisticated and flexible windowing model. It has different kinds of windows. For the second data flow pipeline I built, I used sliding windows. And I mentioned this earlier. It does something that's really powerful. It lets you say, do you want a window by data arrival time into the pipeline, or do you want a window by, and do your analysis with respect to when the data was actually generated? And so we're doing it with respect to when the data was actually generated, when the ship actually emitted that bit of information to the satellite. Otherwise, we wouldn't get good results, of course. Okay, and then the other key piece then is using the CloudML engine online prediction service and the learned TensorFlow model to in our pipeline to actually do these predictions. So you can do this with any TensorFlow model, and you just need to make sure that it adheres to a certain convention when you're building it. This is spelled out in the documentation, obviously. When you're building it, you need to add certain input and output collections to the graph. And you can actually do this kind of post hoc, which is what I did with the Global Fishing Watch model. I took the trained model, I essentially loaded it in to a TensorFlow session, added these new nodes that were necessary for CloudML, and then wrote it out again. So you don't need to do retraining again to add these nodes to your TensorFlow model graph if you've done any messing with TensorFlow. So after you train your TensorFlow model, you have to save it in a certain way. Basically, you need to export it as a metagraph. And then once you've done those two things, then CloudML engine knows how to deploy that model and how to use it, how to serve it for predictions. So that looks like this. This G-Cloud, for those of you who aren't familiar, is the Cloud Platform SDK. So this is command line. You first create your model. That's just kind of like a semantic tag for the model. And then you deploy a named version of that model with a pointer to the path where you saved the model once you were done training it. So you did your training, whether it was on CloudML engine using GPUs, as David's team has been doing, or some other way. You've got your trained exported model. Now you point to that path, and this deploys your model to the cloud. So then once you have done that, and it's successfully deployed, you can use it for prediction. So this is, you can do that in all sorts of ways, and you can do it just from the command line, gcloud ml predict, and just feed it the model input in the form of, like, say, a JSON file. Or you can do what I did in this Dataflow pipeline, is use the CloudML REST API and send it data and call it directly from the Dataflow pipeline and get back the prediction and use it for subsequent processing in the pipeline. So I don't know if any of you caught the keynote this morning and the New York taxi, very cool New York taxi demo. But if you did, you might have caught that it was doing the same thing. It was calling the CloudML engine online prediction service from a Dataflow pipeline. Okay. So just sort of one more dive a little bit further to look at, like, what's the UI look for this? If you're going to build this, what would you see in the Cloud Console? Okay, so here's that pipeline happily running, and you can see the call ML engine part is where we're actually making the REST API calls out to the CloudML prediction service. And then we're taking that information, basically where do we think fishing activity is happening, and the rest of the pipeline is grouping it according to these S2 geometry regions, and then doing a streaming write to BigQuery to record what we have inferred. So here is a dashboard for CloudML online prediction requests. So you can see I'm kind of like cutting it close. I keep coming close to my quota, but I'm carefully backing off when I do. So this just lets you track what's going on with your deployed TensorFlow models. And then this last tab here is BigQuery, where all this derived information is getting written. BigQuery has a streaming API, and then we can use it for whatever we like, including building a map like the one I showed you. So I'm going to try to run this query just to kind of prove that it's a live demo that we're watching. And so the processing time is in UTC, but you can see that it's relative. It's written in bursts. You can see UTC time. That's relatively close to our current time. Okay. So those are just my backup slides there. All right. So if we go back to that design pattern that I was showing you earlier, use Dataflow to do pre-processing, to do feature creation, shuttle that data off to CloudML engine to do distributed training, really highly scalable, use GPUs. Now we can see there's another piece of this that is also very common, is you've got your trained model, you want to deploy it, and then you want to use it for prediction. So that's the sort of the bottom part of this graph. And in the lower left, that's my new Dataflow pipeline, which is using the deployed model through the CloudML API to get those predictions. Okay, so just to summarize what I did with the new streaming pipeline, there were a few cool things that made it all fit together. So the first thing was Beam's unified batch streaming model, right? There wasn't really very much that had to be done before I started building on top of this. So that was one thing. The ability to easily compose pipelines, kind of glue them together using PubSub. Beam's ability to support reasoning about event time in terms of when the data was actually generated, not when it arrived. And then, of course, the CloudML Engine online prediction service to use our trained model in this new pipeline and get results and just incorporate it into the analysis. Okay, so we covered a lot of stuff, and from the cloud platform standpoint, hopefully you've gotten a sense of how you can use these products for real-world problems, in an interesting way. How easy it was for me to build on that and extend and add new functionality without having to do a huge amount of extra work, and that there are some useful design patterns that we talked about that come up again and again when you're building this kind of workflow.
So just want to, I think, so that brings us more or less to the end of our talk, and I just want to take a step back and say why I think this is really exciting, and as someone who's kind of interested in working on big data problems to address the global environment. What's really cool about this is we couldn't do this 5 years ago because we didn't have the satellites, we didn't even have the data set, and even if we didn't have this technology to process it, to be able to do these machine learning techniques didn't exist. And so we're really able to make a huge leap forward now compared to just a few years ago, and that's one of the reasons why I got up and really excited to work on this data set every day, and I think it's going to make a real big difference in terms of how we manage some of these globally shared resources. So. Okay.
So, what's next, basically? First, exciting news from Global Fishing Watch. I will let David.
Yes, we have. So first, we have a data website, globalfishingwatch.io. companion to the .org site, where you can download as much of our data and code that we are able to post there. The main data set of AIS is proprietary. We have to buy it, so we can't just share it with anyone. But the other, but our code and a lot of the derived data, we can share. And so we're making it public there. And also, just today, we have made the repo with this whole vessel classification and fishing identification, all this machine learning stuff we've been talking about is all in that repo. So you can go and do this yourself. And in fact, we even have some training data, which we've anonymized to keep our data provider happy. So you can't get the name of the boat off it, but you can actually use that training data to train the model itself. So we are making some data and the code available, so you can go home and do this yourself.
And then from the standpoint of the technology, if you want to dive into this a little more, there's actually, at Google Next, there's a bunch of code labs, as some of you have probably already discovered. And there are some code labs relevant to this, that I've listed some of them. And you can also just go try them at home at your own pace if you want to. Make a note of that bottom link. And you'll see all the code labs, and you can just go poke around and explore not only these, but the whole range of them. All right, thank you very much.